Today we will finish our discussion of radical chemistry and move on to our next topic, which means we are on our verge between finishing our exam 2 material, and we'll mention when that is later today. All right, so right now we are on page 45, and we'll be entirely in the lecture supplement today, and next time as well. We've been talking about free radical processes, and today I want to talk about one free radical process which is kind of the legacy of mostly my parents' generation, but some of my generation to yours as well. In other words, this is how free radicals is messing up the world for you. So we would like to talk a little bit about CFCs and ozone depletion. Let's talk about ozone first, why we should care about it. Ozone is a molecule which by itself is rather hazardous. It likes to oxidize things. It likes to chop carbon-carbon double bonds, as we talked about last time. But in the stratosphere, it protects us from a high-energy ultraviolet that comes from the sun. And it does so by absorbing these photons in a balanced equation. 2 ozone molecules become 3 oxygen molecules. So this relatively sparse, relatively diffuse layer of ozone protects us from this high-energy ultraviolet. Why is that an issue? That high-energy ultraviolet can do other chemistry. We talked a little bit about photochemistry, and that can lead to DNA damage and that kind of thing. And so it's been argued that the presence of the ozone layer has actually allowed complex life to evolve on Earth. In the absence of the ozone layer, organisms would just never have been constantly mutated, probably never would have become very sophisticated if they would have survived at all. Now, enter the CFC portion. CFCs, chlorofluorocarbons, these are molecules which, as the name implies, have chlorine, fluorine, and carbon. They're of interest because they were used as refrigerants and propellants in spray cans and things like that. And they were used because these substances have low chemical reactivity. In other words, if you have something in your refrigerator, which is the thing which is taking the heat out of the place where your food is, and it's in there for a long period of time and it's under pressure, you don't want it to be something that's going to be reactive and chew up the copper tubing. So these molecules, pretty unreactive. On top of that, they also have a high heat capacity, which means that per mole they can absorb a lot of heat. Now, in terms of their low chemical reactivity, if they're released into the atmosphere, you can see where this is going because we're talking about ozone, their half-life is typically 50 to 100 years. So that means when you take your spray can and go, psh, 50 years from now, half of that is still around because this stuff is chemically inert. It does virtually nothing in the lower atmosphere. It doesn't dissolve in water, so it doesn't rain out, so on and so forth. So most of it makes its way up to the stratosphere. Now, when it doesn't really, as I said, doesn't do much of anything until it gets into the stratosphere, high level, maybe 8 to 50 kilometers. And people ask, what happens to it in the environment? And particularly 3 people. Christian, who is in Germany, Roland, who was and still is at UCI, and Molina, who was a postdoc with Roland at UCI, and Molina is now at MIT. We're interested in studying what happens to this. So to make a long story short, they found out that when CFCs go into the atmosphere, up into the stratosphere, they interact with this H nu and destroy ozone. That's a problem. So what do? They're causing destruction, depletion of ozone, principally over the South Pole and to a lesser extent the North Pole, causing what's called the polar ozone hole. It's an area where ozone concentration has been significantly depleted, and because the ozone concentration has been significantly depleted, much more of this high-energy ultraviolet can get through. Now, if you're an organism living in that area, let's say a penguin, since we're talking about the Antarctic, you might be prone to skin cancer and that kind of stuff. Now, maybe people say, okay, fine, penguins, no big deal, right? Who cares if penguins get skin cancer? Well, if you'll notice the size of these holes, now these are false color images, but they're created basically by satellites that measure the amount of ozone, and this gray area represents a place where the ozone is significantly depleted. And these holes, over the years, were getting larger and larger and larger, and moving over to places like the southern tip of South America. You can begin to see it here. Places where people are. And so we don't want no ozone over where people are. And these holes get pretty big. The biggest one on record actually was in September of 2006. So One of the questions is, why does this only happen over the poles? And it has to do with the actual reaction, the ozone destruction mechanism occurring on ice crystals, and that happens only over the poles. The cold poles has something to do with that. And what's the connection between CFCs and ozone? Well, what it was figured out was the presence of the CFCs were destroying the ozone through a free radical process. We're going to talk about the mechanism for that in a second. And so the world got together in Montreal in 1987 and said, CFCs are a bad thing, we have to ban them. And CFC manufacture and use was phased out. More technologically sophisticated countries had their ban earlier. So the United States, for example, and Japan were basically immediate. Countries like Mexico were later on. So as the amount of CFCs in the atmosphere decreased, it's going to take a while. Remember, these things have a long half-life. But as the amount of CFCs decreased, ozone hole got smaller. Everybody patted themselves on the back and said, Yahoo, we solved the ozone hole problem. And consequently, the guys we've mentioned earlier, Crutzen, Rowland, and Molina, received the Nobel Prize in Chemistry in 1995. And it's obviously something that has impact on the world, so that's why they got a Nobel Prize. Well, as it turned out, as the amount of chlorine in the atmosphere, and that's what they measure, as the amount of chlorine in the atmosphere goes down, it's still continuing to go down, ozone hole gets smaller and smaller, and then it starts getting bigger and bigger. So while the CFC removal from the atmosphere may have reduced the ozone hole problem, it also may be a natural phenomenon where the thing gets bigger. We don't know. We only have data for a few decades. It's like a global warming kind of issue. Maybe it's happening. Maybe it's not. We don't know. All right, so where is this coming from? And why can relatively small amounts of material, granted it's probably billions of pounds, but relatively small amounts of material influence something huge like the atmosphere? Well, it's because it's a chain process, and that's what's so insidious about this. And we're going to talk about the mechanism by which ozone is destroyed. And this is a simplified mechanism. We're leaving out a few aspects, like the fact that this has to occur on the ice crystals and so forth. If you go to the internet and search for ozone depletion mechanism or something like that, you will find an awful lot of detail. This subject has been studied pretty heavily. So the process starts with one of our fluorochlorocarbons, this one called Freon 12. You may be familiar with Freon. That's the trade name for these things, and the numbering after them is a code which has to do with the number of carbons and fluorines and chlorines and so forth. When this thing is photolyzed, so it reacts with, it absorbs the high energy ultraviolet photon, we get a covalent bond breaking step, homolysis of that, so we get a carbon radical and a chlorine radical. Now the carbon radical turns out to not be the issue here. That's removed from the cycle. It doesn't really do anything bad. It's the chlorine radical that's the problem, because the chlorine radical, when it's up in the stratosphere, finds an ozone, and there's one way of drawing ozone. There's alternate resonance contributors you can use, but a diradical one's good for this. So chlorine reacts with the ozone, two radicals come together, or excuse me, the chlorine's going to remove an oxygen from the ozone to make ClO dot and O2. So that's one of our standard radical mechanism steps. It's an atom transfer step. Now the ClO, two of those come together to make ClOCl. And you might say, wait a minute, this looks like a termination step. And it also looks like a step that we said was rare, because this is two radicals finding each other. And that is true, it's rare, but remember this happens on the surface of the ice crystal. So there's the ClO radicals tend to accumulate there, and there's a greater possibility they can find each other. You can, if this metaphor works, the ice crystal is the Facebook, or is any of them, Match.com for radicals, whatever you'd like to think of that as. So these two guys come together to make ClOCl, and we know that oxygen-oxygen bonds are relatively weak because of all that lone pair repulsion. So that can come apart, or the oxygen-chlorine bonds are weak for the same issue. So we now have breaking an oxygen-chlorine bond, the ClOO dot plus Cl dot. And then the ClOO dot can lose another chlorine to make oxygen and another chlorine. But there's something I want to point out here. The overall process is chlorine reacts with ozone to make oxygen plus chlorine radicals. So the chlorine radical can cycle through and destroy another ozone, produce more chlorine, which destroys another ozone, etc. So because this is a chain process, one from your spray can can destroy an awful lot of ozone. Now, if you'd like to think of it from a somewhat different point of view, there was a day when CFCs were used in car air conditioning, and if you needed to have your CFCs recharged, what you would simply do is pull the car in the garage and they'd open the little valve and take any CFCs that were left and just release those into the atmosphere. Maybe it's only a pound. And that went away into the atmosphere. Now, how many moles is a pound when you're talking about this kind of molecule? And how many cycles is that going to go through? So 1 pound of CFC could destroy tens of thousands of moles of ozone, an awful lot. And the typical turnover number, that's the number of cycles that it goes through before it gets terminated, on average is maybe about 10 to the 4th. So that means that one chlorine atom can destroy something like 10 to the 4th ozone molecules on average before that chlorine gets removed and the chain gets terminated. So that is an issue. All right, now, our last radical topic we're going to talk about, and you might say, no, I don't want to hear anymore. But in fact, that's exactly what we're going to talk about. NO, nitric oxide. Not nitrous oxide, that's different. So NO is interesting because it is a free radical. Although this one doesn't have carbon in it, it's still a biologically important one. And it's a free radical because it has an unpaired electron on the nitrogen. Important because it's gaseous, it's an air pollutant, it's one of the things that helps make our ugly, nasty brown photochemical smog here in LA. Also, it is implicated in ozone destruction in high altitudes by pretty much the same mechanisms as the chlorine radical. An issue because NO is something which is produced from jet plane exhaust, especially the Concorde, speaking of the legacy of previous generations to yours. The Concorde, which flew very high. If anybody ever see pictures of the Concorde taking off? That ugly brown plume behind it, a lot of nitrogen oxides in there. So when you're doing that at high altitude, you're releasing NO in the vicinity of ozone, and that's a problem. But NO is also interesting because it is a cardiovascular signal molecule, which means it runs around the body and tells the cardiovascular system what to do. This particular fact, one of the things that it does is it causes relaxation of blood vessel wall smooth muscle, in other words, vasodilation. It's kind of surprising that a molecule like this would be used as a signal molecule for a couple of reasons. Number one, it's a little molecule. It's only 2 atoms. It's not the fact that it's physically small. It's the fact that it's simple. When we think of signaling molecules, generally we want them to do a specific task. And often specificity means complexity when it comes to the biological world. So NO dot you don't think of necessarily as being a good signal. Number two, it's a radical. I mean, we talked about radicals doing biological damage. What organism in its right mind manufactures free radicals to use for signal purposes? It's like saying to someone, okay, we want you to go outside and signal people. Here's a loaded shotgun. Use this to signal people. Now, if you use it right, I suppose, but it's kind of dangerous. But it's pretty short-lived, only about maybe 10 seconds in vivo in the organism half-life. Now, the biochemistry of this molecule was studied by a couple of people. The one of interest that I want to mention here is Louis Ignarro, who is a professor in the physiology department, as I recall, in the med school. And they studied NO and what does it do, how it operates, etc. And based upon their work, some anti-angina drugs were being explored. Drugs that would release NO so to minimize heart pain and so forth. And consequently, for their work, they won the Nobel Prize in Medicine for 1998. But there are also other physiological effects associated with NO. Some of them are listed up here. But one of them has to do with blood pressure, blood flow, that came out of a side effect, a surprising side effect, that got the attention of some people who were interested in these cardiovascular drugs that turned out to have a much, much, much bigger market. Anybody know what I'm talking about? Viagra. Viagra essentially came out of this research. So we could argue that Viagra wasn't invented at UCLA, but it certainly has roots here at UCLA. And somebody recently pointed out to me, they said, I already know that. We're like blue and yellow, and it's the little blue pill. So of course it came from UCLA. All right, but anyway, so be aware that that is another free radical kind of process. All right, so at that point you can make a little line in your notes and say that's our end of exam 2 coverage stuff. So what I'm going to start talking about now, which is the beginning of our long exploration of carbonyl chemistry, this not on our second exam, this is on final. All right, carbonyls. Now, we're going to spend a good portion of the remainder of what we do in this course talking about carbonyl reactions in one form or another. Now, if you've looked at molecules and thought about reactions, it makes some sense that we're going to spend a lot of time doing that because there are a lot of carbonyl-containing functional groups. And carbonyl-containing functional groups especially important in biology. What holds proteins together? Amides. What do carbohydrates have? Aldehydes and ketones, that kind of stuff. So there's a lot of carbonyl chemistry out there that's important. So in essence, we're going to talk about the chemistry of the carbon-oxygen double bond with other stuff on the side of it. Now, because there can be all sorts of other stuff on the carbonyl, there's a whole bunch of carbonyl functional groups that are possible. And we're going to lump these all together because we know that similar functional groups have similar arrangement of atoms, similar polarity of bonds, and so forth. And those kinds of issues, bond polarity, how many lone pairs there are, is it a single bond, double bond, etc. Those kinds of issues define the way functional groups behave. So in other words, all the carbonyl-containing functional groups are going to have many similarities in their chemistry. Not completely the same in all cases. Aldehydes are a little bit different than ketones, but a lot of what aldehydes do, ketones will do as well. So that's why we lump them all together. So in terms of carbonyl-containing functional groups, what do we have? This is an incomplete list, certainly, but it's the most common ones that we see. There's aldehydes. We know are a carbonyl with a hydrogen on one side and some sort of carbon group on the other. A ketone is like an aldehyde, except that it's 2 carbon groups, so we expect a lot of parallels between aldehydes and ketones. Carboxylic acids have a carbon group on one side of the carbonyl and then an OH on another. So we expect some differences between ketones and carboxylic acids because of that OH, but some similarities because they both have a carbonyl. Carboxylates are the conjugate bases of carboxylic acids, and a lot of textbooks don't treat carboxylates as their own separate functional group. We will, because the presence of that O- does some things to carboxylates. They end up being the least reactive pretty much of all of them because of that O-. As we go through mechanisms and reactions, we'll see why that is. Then there are esters, of course, which are strongly related to carboxylic acids because an ester has an OR, whereas a carboxylic acid has an OH. So we expect lots of similarities between esters and carboxylic acids. That's true, except where the OH bond is involved. Thioesters are like esters. Thio means sulfur, so it's got a sulfur instead of the oxygen. Again, parallels between esters and thioesters, but not quite exactly the same, because SR, for example, is a better leaving group than OR. Then we have amides, and we're going to talk about amides in 3 different flavors, primary, secondary, and tertiary. And what do you think differentiates those? Think about when we've talked about primary, secondary, and tertiary. What's the difference between a primary and secondary and a tertiary carbocation, or a primary and secondary and tertiary alkyl halide? It's the number of carbons attached to the thing we're talking about. So in a carbocation, it's the number of carbons directly attached to the carbon that bears the positive charge. In an amide, it's the number of carbon groups directly attached to the nitrogen. In a primary amide, the one carbon group is the carbonyl. In a secondary amide, it's the carbonyl plus another one. A tertiary amide has the carbonyl plus 2 R groups on the nitrogen. Then we have anhydrides, which are unique among our carbonyl-containing functional groups because it's the only functional group that's got 2 carbonyls in it. It's like the Richard Nixon of functional groups. I am not an electrophile. Remember back to 14C when we talked about Richard Nixon? Right? All right. It's called anhydrides, by the way. Anhydride is like anhydrous without water. Anhydrides are named that way because a common way to make them is to take 2 carboxylic acids and bring them together. It's simultaneously taking out a molecule of water. And then there are acid chlorides, also called acyl chlorides. These are related to carboxylic acids, except they have a chlorine instead of an OH. Now again, there are other carbonyl-containing functional groups, but these are the ones we're going to run into the most. What I want to do to introduce our study of this topic is to start by looking for fundamental patterns in reactions and reactivity. how they react, why they react, etc. By doing this, it will make our study of carbonyls easier. If you have read the textbook, which by the way is a fine textbook, but if you've read the textbook, you will find that it tends to talk about this functional group and this functional group and this functional group and this nucleophile and this nucleophile, and you have a whole long list of reactions. Well, you don't need that. I'm not saying the way the textbook does it is wrong. I'm saying we're going to do a different approach. Our approach is going to be to look for patterns. Now, if you like patterns, you'll love carbonyl chemistry because there's lots and lots and lots and lots of patterns. There are differences. There are details. But patterns make this easier. If, on the other hand, you are a memorizer, your head is about to explode. Because, just make sure you wipe up when you're done, okay? Because there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbonyl-containing functional groups that we're going to talk about. Add to that how many different kinds of nucleophiles there can be. Add to that the fact the reactions can be neutral or acid catalyzed or base catalyzed. So 11 times a lot times 3. If you are a memorizer, I'm hoping that's going to dissuade you. Because if you are not a memorizer, if you're a pattern looker for, a pattern seeker, you will discover that there are fundamentally just 2 carbonyl mechanisms, addition and substitution. And that's it. There's variations on them. It depends what the nucleophile and the leaving group and so forth is. But look for the patterns. It will make your life much, much, much easier. All right, so let's find patterns. Let's start by talking about the fundamental carbonyl group. What's its structure? How is it going to behave in a mechanism at all? This is kind of like thinking about carbocation fates. So first of all, let's talk about its structure. Now, obviously, the carbon-oxygen double bond doesn't have geometry to it. But imagine we're talking about, let's say, a ketone. So there's carbon groups out here. How would you describe the geometry of that portion of the molecule? It's trigonal planar. The carbon is sp2. The oxygen, the carbonyl carbon, and whatever is immediately attached to that carbon all lie in the same plane. So this guy is planar. Now, what about the way it reacts? Can a carbonyl, most of the reactions we've seen involving nucleophiles and electrophiles, as it turns out, radical reactions occur in carbonyl chemistry, but they're not as important as nucleophile-electrophile reactions. So let's look at this guy and say, how would we decide whether a carbonyl is going to be a nucleophile or an electrophile? What things do you look for when it comes to being, let's say, a nucleophile? Electron density, right. But what do we look at in a molecule and say, aha, this molecule has a this, or a this, so it's a nucleophile? Lone pairs, formal negative charge, and delta minus. Well, this guy has no formal negative charge. Everybody in the carbonyl has got exactly the right number of electrons. There are, however, lone pairs. There's also pi bonds. Both of those are potential sources of electrons. And on top of that, the carbon-oxygen double bond is polarized. How is it polarized? Which atom is more electronegative, oxygen or carbon? Oxygen. So which atom of the carbonyl gets the delta minus? The oxygen. So those three things together that we've talked about, lone pairs, pi bond, plus the delta minus, delta plus polarization of the carbonyl, says that this thing can behave as a nucleophile, and it will like to react with electrophiles. So let's say we use the lone pair for that. So that's one possibility. But the carbon has a delta plus. So what does that suggest? It says that in addition to being a nucleophile, the carbonyl can also be an electrophile. It's got a delta plus. Nucleophiles will like to go to that delta plus carbon. So therefore, the carbonyl group can have both nucleophilic properties, where it reacts with electrophiles, and it will have electrophilic properties, where it reacts with nucleophiles. Now, we're going to see both of those occurring in mechanisms. But I will tell you that every single carbonyl mechanism that we do for the next several hours together, every single mechanism will have nucleophilic attack at that carbon. Not all of them will have electrophiles going to the oxygen end, but every one will have nucleophilic attack at a carbonyl. Every single one. All right. Now, knowing about the polarization of the carbonyl, we can begin to think about how a carbonyl containing functional group will behave in a mechanism. Now, this is exactly the same thought process we went through when we came up with fates or a carbocation. We said, okay, we've made a carbocation. How will it behave? What are its choices? And how it behaves depends upon its circumstances, its anxieties, if you will. So we said a carbocation has that open octet and positive charge. It likes to get electrons. So carbonyl, because of its delta plus on the carbon and delta minus on the oxygen, will have also fates. And what we mean here is if there is a carbonyl present at the beginning of the mechanism step, what are its possibilities? We're not defining entire mechanisms here. We're simply defining carbonyl's choices. What might it do? Well, number one, we said the carbon has a delta plus. So that means nucleophile can attack there. The carbon can accept the nucleophile. Now, this happens not only because the carbon has a delta plus, but also when this nucleophilic attack occurs, which we have here, a nucleophile going to the carbon. Of course, the carbon has 8 electrons to begin with, so it's got to sacrifice a pair. We'll give those to the oxygen. The fact that oxygen is so highly electronegative and can readily accept that pair of electrons helps this process along. So that oxygen's electronegativity is really doing two things: giving delta plus to the carbon and helping shift the electrons towards the oxygen when the attack occurs. Now, like I said, this step, nucleophilic attack of the carbonyl, occurs in all our carbonyl addition and substitution mechanisms we're going to talk about. This is almost the equivalent of back in Chem 14C when we were talking about IR. I said if there's one thing you learn in IR, it's how to find a carbonyl. So if there's one thing you learn in carbonyl chemistry, in reactions, is to do nucleophilic attack on the carbonyl. If somebody wakes you up in the middle of your sleep and says, quick, I'm a carbonyl, what are you going to do? Nucleophilic attack. I hope people don't wake you up in the middle of the night and ask you that. But all right, so this attack leads to an intermediate in which or perhaps a product, but where the nucleophile has come in to make a new bond and the carbon-oxygen pi bond has gone away. So the carbonyl-carbon hybridization goes from sp2 trigonal planar to sp3 tetrahedral. And consequently, we call this thing the tetrahedral adduct. Some textbooks call it a tetrahedral intermediate. It's not always an intermediate. Sometimes it's the last step in the mechanism and then it's the product. So that's why I avoid that word. But tetrahedral adduct, so addition product. And again, it's called the tetrahedral adduct because we're going from sp2 to sp3. So that's one possibility. And here, by the way, I've shown it going from a neutral carbonyl to an O-. There'll be times when the carbonyl's got a proton on it, so this will become an OH. We'll see that later when we get there. All right, another possibility in terms of carbonyl fates is reacting with an electrophile at the carbonyl. Most of the time, the electrophile is going to be a proton. There are some exceptions to that, especially in biological systems, where sometimes metal cations will be in the vicinity of the carbonyl and do the same thing. So if you wondered, for example, why you have to have magnesium, it's because magnesium catalyzes some of these processes by doing this kind of thing. So how does this work? Well, let's see. This is assisted by the lone pairs and the pi bond. Of course, there's our pi bond and our lone pairs, both of which can give electrons to the electrophile, which is usually a proton. And if we are putting a proton on, the protonation requires strong acid. H2SO4, HCl, HBr, or aqueous strong acid, i.e. H3O+. Weak acids, like water by itself, not sufficiently acidic to protonate a carbonyl. To protonate a carbonyl, you need strong acid. You need stuff like sulfuric acid, strong acid. But when we draw out the curved arrows, we have a question. We said the lone pairs and the pi bond are both potential sources of electrons that we can use to make the reaction with the electrophile, in this case, the proton. So which do we use? Well, let's explore that. Let's start by putting the proton on the lone pair. So there's the lone pair. We're taking the proton. B is just some generic conjugate base here. We don't know what it is other than the fact that it must be a weak base, so that HB is a strong acid. All right, so there we put the proton on the carbonyl. Or we can use the pi electrons to take the proton. We've seen examples of pi electrons taking protons. We just talked about H3O plus and HBr and things like that, adding to alkenes and alkynes. Because this is an unsymmetrical pi bond, then we have to ask ourselves the same question we had to ask before. Which end does the proton go to? If we put the proton on the carbon, then we take the electrons away from the oxygen. We end up with an oxygen with 6 electrons and a positive charge. Not so good. Or if we put the proton on the oxygen, we end up with a carbon and an open octet. Also not good. Which one of those would you rather have? The second one, you want this structure, the proton, put the proton on the oxygen to put the positive charge on the carbon. That's the one you want? Okay? Unlike religion or politics, you have to have facts to back up your opinion. What's your fact? Why this one?
It's a secondary carbocation.
Okay, it's true, it's a secondary carbocation, but why is a secondary carbocation necessarily better than an oxygen, which has the same issue, the positive charge in the open octet? You're kind of along the right line. Yeah, the answer to every question in the organic chemistry universe is resonance. This guy doesn't have resonance. This guy does. Lone pairs next to open octet. That's a standard resonance. We've seen this before. Lone pairs stabilizing a carbocation. I'll give you a second to draw in your think book. Draw the resonance, the other resonance contributor for that. Oh wait, you're done. That's all the time you need. Because it's already drawn for you. Right up here. Tricky, tricky. There's a reason it's done that way. So we can answer the question, do we put the proton on the lone pair? Do we put the proton on the pi bond? Or does it not matter? You're shaking your head no. We don't protonate anything? It doesn't matter. Unlike religion or politics, what's your fact? But they're resonance contributors. It's the same. That's exactly the point. Resonance contributors are alternate ways of drawing exactly the same molecule. So whether you put the proton directly on or whether you use the lone pairs and it leads you directly to the oxonium ion contributor, or you use the pi bond and it leads you to the carbocation contributor, it does not matter. They're representations of exactly the same molecule. So it does not matter whether you draw the curved arrows coming from the lone pair or the pi bond. Now, I will tend to draw them coming from the lone pair because it just looks a little better, because it leads to the more significant resonance contributor directly. But it does not matter. It is a moot point. Use either one. All right, so conclusion, doesn't matter. Use either one. On the bottom of the page, we have the third carbonyl fate, which we're not going to talk about so much in the beginning, because we're going to focus more on this after we're done with addition and substitution reactions. And that is the formation of an enolate. Now, this is a process in which the proton on the carbon next door to the carbonyl, we call that the alpha carbon, because it's right next to, remember alpha and beta when we talked about beta elimination? So relative to the carbonyl, this is the carbon that's right next door. That's the alpha carbon. So we take the alpha hydrogen away. And it's not because it's the boss carbon, right? It doesn't like have a silver streak down its back like a gorilla. You know, the silverback gorilla, alpha male. He's the one in charge. This carbon doesn't go around bullying other ones so it can mate. That's not what this is. It's alpha because you haven't taken biology yet, have you? The chemistry majors understand that joke better than you guys do. All right, anyways. So this is, by removing this, we get a structure which has a negative charge on the carbon, but because it's a lone pair next to the pi bond, we have nice resonance stabilization. So the combination of these resonance contributors is called the enolate. There's the hybrid, if you like. And that actually has very important uses in making new carbon-carbon bonds, but we're going to talk about that later. Now, having talked about carbonyl fates, we can take one step further back and look at a somewhat larger picture in terms of mechanisms and come up with generic, general carbonyl mechanisms to say what combination of steps gives what general outcomes. So if we start with our nucleophilic attack at the carbonyl, that takes us up to a tetrahedral adduct with a negative charge on the oxygen in this particular case. Now, oxygen likes to be, like all other atoms, likes to be neutral. You've given it negative charge. It wants to get rid of the negative charge. So it's going to seek to do that in a couple of ways. Now, one of the ways it can do it is by reforming the pi bond, or it might accept an electrophile, usually a proton, at the oxygen. Which one of those pathways do we look at first? Let's talk about that decision before we talk about the products of the pathways. We actually have a rule that we've already developed, but I will repeat for you here in a second. We have a rule that basically says which one of these pathways we look at first. This pathway occurs within the molecule, intramolecular, and this pathway requires a second molecule to come along and deposit that proton, intermolecular. We talk about favoring intra versus intermolecular. I don't know whether or not we did, so I'll mention it again, partly because it involves physical pain to myself, and I know that will please you. True story. This is a metaphor, but it's a true story. When I first came out to California in 1990, shortly after I got married, so this was like the early January 1991, my brand new wife and I went to Hollywood to do a touristy thing. We went to a comedy club. Now, we happened to go with, we got invited by the people that she worked for, which was Caltrans, and so we ended up getting there a little bit late, and they saved a table for us, which was really nice. It was right next to the stage, so we could see the comedian right there. And I thought, wow, this is great. They saved a table for us. If you've ever been to a comedy club, there's a reason why the only seats that are left are front and center, right? Because those are the abuse seats. So we sat through the show, and I got personally abused by the guy who does the voice of Roger Rabbit, but that's a whole other issue. He was the main line that day. Yes, he did chemistry jokes. Nobody laughed except me. So we leave the club at about 2 a.m. We're coming back down the 101 because we lived in Orange County at the time. Coming back down the 101. And at 2 a.m. on a Sunday morning, I knew that I was now officially a citizen of Los Angeles. Because at 2 o'clock on Sunday morning on the 101, what do you think happened? Traffic. So traffic slows down to a crawl. All right, so I'm driving. Now, at this point, and guys, back me up on this, all right? My wife is sitting next to me in the passenger seat, and I have no clue what I said. But she wanted to cause me physical pain. I have absolutely no reason why. Now, at the same time, about one lane over and maybe 100 feet back is a drunk in a pickup truck. And I figured he's drunk because he's kind of trying to weave it in and out. So at that point, that instant in my life, there were two people that wanted to cause me pain. My wife sitting right next to me, who only had to go whack. Or the guy in the pickup truck who had to come through the rest of traffic before he could go whack. Who do you think whacked? It sounds like a mob movie. Who do you think caused me physical pain first? My wife. She was sitting right there. She didn't have to move through other people, other cars to get to me. So the moral of the story is, if there can be one said, is things within the molecule tend to occur faster than things between two molecules. Because for two molecules to react, the molecule kind of has to swim through solvent to get there. So a good operational rule that we've used in the past, and we're going to continue to use, is the processes within the molecule, intramolecular, generally faster, intramolecular, within the molecule, generally, not always, generally faster than between two molecules, intermolecular. Again, there are exceptions, but it's a good operating rule. So that means when we have a tetrahedral intermediate with a negative charge with the oxygen, and that tetrahedral intermediate is striving to get rid of that negative charge, the fastest way to do that is going to be the intramolecular process, which is the ejection of the leaving group. So in other words, this, reform the carbonyl, leaving group leaving, takes us up to here. Now, the tetrahedral intermediate is generally going to kick out, of course, the best leaving group leaves first. If the best leaving group is the nucleophile that came in, the tetrahedral intermediate just goes back to where it came from. Nucleophile in, nucleophile out. You know, proton, or excuse me, wax on, wax off, right? Nucleophile in, nucleophile out. But if the thing that was already attached to the carbonyl, this thing X, if that's a better leaving group than the nucleophile, or every now and then, the X group, the thing that was already attached, leaves. We reform the carbonyl, but instead of having the X group, we've replaced that with the nucleophile. The net effect is substitution at the carbonyl carbon. So we call that generic process nucleophilic carbonyl substitution. Many textbooks call it nucleophilic acyl substitution, and that's a bit of a misnomer because an acyl group is a carbonyl with a carbon group next door. And this doesn't have to have a carbon group next door. It often does, but it doesn't have to. So that's why I think acyl is a bit of a misnomer there. Now, what happens to the tetrahedral adduct if the nucleophile and the X group are not good leaving groups? So no possibility to go backwards or forwards. Well, then the oxygen seeks to get rid of its negative charge by doing something else, usually accepting an electrophile, most of the time a proton. So the net effect is addition, where you've added nucleophile plus a hydrogen across the pi bond. And these, right here, are your generic carbonyl mechanisms. I could at this point say, okay, go home, you know almost everything you need to know about carbonyl reactions. Because that's it. That box represents the vast majority of carbonyl mechanism processes. We're going to do dozens of reactions, but they're pretty much going to fall into one of those two categories. Now you might say, well, in terms of the substitution, why do we do this additional, it's commonly called the addition elimination mechanism, addition to the pi bond and then elimination of the leaving group. Why do we do that for substitution? Why don't we just do a direct SN2 kind of process at the sp2 carbon? It turns out that that doesn't happen. It's a combination of steric hindrance, the way the orbitals are arranged, but it just doesn't happen that way. We don't see direct substitution processes ever at sp2 or even sp carbons. sp3 carbons, yes, but not sp2. Now, these two mechanisms are going to happen for different carbonyl functional groups because the substitution requires a leaving group of some sort, and addition occurs when there's no leaving group. So we can extend that and say, all right, substitution occurs again when the carbonyl bears a leaving group, and that's going to be for esters, amides, anhydrides, acid chlorides, etc. The only two that won't undergo the substitution are aldehydes and ketones because they don't have leaving groups. There are certain ketone cases where it can, but that's a very specialized reaction we're not going to worry about. So for the most part, aldehydes and ketones do addition. Everything else does substitution. And this, as it says here, is kind of your generic mechanism recipe. You can create pretty much every single carbonyl addition or substitution mechanism by doing nucleophilic attack, fate of the tetrahedral adduct, and then add proton transfers. And then, as a student once said, stir. It's like a recipe, right? You put in spices to taste and kind of stir it up. Throw in a band if you need to, if you're an Emerald fan. Anybody an Emerald fan? Yeah? Anybody watch Rachel Ray? Guy Fieri show? Anybody know Guy Fieri show? Isn't he nuts? Yeah. Guy Fieri, he does a show called Diners, Drive-Ins, and Dives. So he goes around the country to a whole bunch of different restaurants and samples all sorts of interesting things. He ate pig ears the other night, which he didn't really want to eat. All right, so here's some examples of the generic process. If we take a ketone and react it with water, now this is a ketone. It has no leaving groups. Methyls are never, ever, ever, under any circumstances, are CH3 minuses leaving groups. So water will do the addition. The net effect is the addition of HOH across the CO pi bond. On the other hand, here's an acid chloride. Chlorine is a leaving group, so water will do a substitution for that. And the net effect is to replace chlorine with an OH. And I'll leave you to work out the mechanisms for that, although once we start getting into the reactions, that will turn out to be pretty easy to do those two. All right, so now that we know the generic mechanisms, now we're in a position to ask a question, what about relative rate? Do aldehydes and ketones react at the same rate? Do acid chlorides and amides react at the same rate? It's an important issue to know, so let's talk about where that comes from, how we can do some predictions. We're going to do the addition rate first because it's a little bit easier. Good place to start. Now, there are different kinds of carbonyl-containing functional groups, of course, so they're going to react at different rates. But again, we're talking about addition, so right now we're just comparing aldehydes and ketones. And as an example of that, let's ask which addition reaction would be faster. Here we have an aldehyde. Here we have a ketone. And we're going to do addition of methoxide, CH3O minus, and there's our proton source OH. So we add in both cases, and we're going to focus on the rate. Now we're making a comparison, comparing rate of aldehyde reacting with rate of ketone. The nucleophile is the same, the solvent is the same, etc. So what we need to do is we need to focus on what's different. But also, because we're talking about rate, we need to think about the rate expression, which means we need to look at the mechanism. And if it's a multi-step mechanism, we need to figure out which step is rate determining. Now this is a multi-step mechanism. There's essentially two steps. There's our nucleophilic attack on the carbonyl. Did I not say that every single carbonyl reaction we will talk about is nucleophilic attack on the carbonyl? There it is. It gives a tetrahedral adduct. Now this tetrahedral adduct has a negative charge on the oxygen, and I'm going to ask a question that you're going to hear many times. I'm going to ask it now for the first time, and you'll hear it again and again and again. This is a tetrahedral adduct with a negative charge on it. What does it do? Carbocations have 3 things on their to-do list. A tetrahedral adduct has 2 things on its to-do list, especially if it has a negative charge. Oxyanionic tetrahedral intermediate. So O minus, oxyanionic. Negative charge of the oxygen. What does it do? It's got 2 things, but it does things in order on its to-do list. The first thing on its to-do list is, go back to the previous page, look at that big red box, or whatever you box, or whatever color you put it in, or circle it, or put a post-it note there, or took a picture of it with your cell phone because it was important. Whatever you did, what does it do first? Now, substitution is a whole mechanism name. Right now we're just talking about one mechanism step. Its choice is eject a leaving group or accept a proton. Which does it do? It tries one first. One is faster than the other. Eject a leaving group, because that's the intramolecular process. So that's what we look at first. So otherwise, can this thing eject a leaving group? Now I know the protonation is shown here. That's because the eject a leaving group, first question is we have to ask, can it happen? And if it can happen, is it productive? So let's address the can it happen issue. I'm going to put it over here so I have more space. In this case, it's an OCH3. Now, the question we're asking is, can this happen? Normally, we would probably say no, because the leaving group, in this case, would be OCH3 minus. Can OCH3 minus be a leaving group? In the beginning of the course, we said no until we get to the special circumstances. Now we're at special circumstances. Woohoo! My life is complete. But the reason for this, the reason OCH3 minus can leave here, is very much like the same reason why an oxygen-oxygen bond in something like hydrogen peroxide is weak. What did we say made the oxygen-oxygen bond in hydrogen peroxide weak? Lone pair repulsion. There's a lot of lone pairs. In the hydrogen peroxide case, we have 2 oxygens with a lot of lone pairs next to each other, and there's a lot of electrons repelling each other. What do we have here? 1, 2, 3, 3 lone pairs there, 2 lone pairs. A lot of lone pairs in the vicinity, so there's some repulsion. That's one of the things that assists the OCH3 minus leaving. But another thing is if we draw the transition state, we can begin to see this. There's the OCH3 leaving. So in the transition state, this has a delta minus, and the oxygen beginning to form its pi bond has a delta minus. So another reason is this formal negative charge gets delocalized, shared, by 2 highly electronegative atoms. And that also assists achieving the transition state. So it's a combination of 2 things, electron repulsion and shared negative charge. So our rule here is going to be an oxyanionic tetrahedral intermediate. That means a tetrahedral intermediate which there's an O minus. O neutral doesn't work. It's got to be O minus. Can kick out something like this, an OR leaving group. It can kick out OCH3 minus, OH minus, etc. So oxyanionic tetrahedral intermediate can kick out an oxyanionic leaving group. We will see later on, not today, but later on another circumstance in which that kind of thing can happen. All right. So that's why this thing can revert, it can go back, but it's not productive. It's not moving it forward. So that only other choice then is to accept a proton. So we're taking a proton here from methanol that leads to the addition product. All right, so here's what I want you to do since we're out of time for today. Two-step mechanism. So we need to figure out which step is rate determining. And then we have to look at that step and analyze rate of aldehyde process versus rate of ketone process. So why don't you work on that? And that is where we will pick up on Friday.